Prior to understanding the concept of rotatory motion, in this situation, the vessel or the body moves in the same direction in which the force is applied. It is said to be linear motion. If the same body continues to move to and fro about the mean position, it is said to be oscillatory motion. Whereas the same body moves in a curved path or a circular path about a particular point, it comes under the category of rotatory motion. Consider the motion of the blades of an electric fan. When it is switched on, different particles are at different distances from the axis of rotation, travel with different speeds. Now observe this flower vase. I am applying the force in this direction. The flower vase also moves in the same direction, therefore it is in linear motion. When the object is in linear motion, all the particles present on this flower vase are parallel to each other and move with same velocities. If I apply the force on one of its ends, it rotates about the axis. The tendency of such a force cause the rotation about an axis depends on the magnitude of the force applied and the perpendicular distance between the line of action of force and the axis. Consider the opening of the door. The vertical line passing through the hinges is called axis of rotation. If we apply a force at the edges of the door, it is easy to rotate. If we apply the force at the edges of the door, it is easy to rotate. If we apply the force at different points, we find it difficult to open or close the door. We find it difficult if the point of application of force is nearer to the axis of rotation or hinges. If the force is applied exactly on the hinges, we cannot move it or we cannot open or close the door. Therefore, it can be observed that turning effect depends not only on the magnitude of force, but also on the line of action of force joining the axis of rotation. In case of rotational motion, a body free to rotate resists change in state of rest or uniform rotational motion of the body. This opposition to rotational motion of the body is called rotational inertia. It's visual. Let us see the rigid body which is rotated about an axis. We can see here three particles M1, M2 and M3 which are at distances of R1, R2 and R3 respectively. Therefore, moment of inertia of any particle about an axis is mass of the particle into square of the perpendicular distance between the particle and the axis of rotation. Let us assume that there are n particles. Therefore, moment of inertia about this axis of rotation I is equal to m1 r1 square plus m2 r2 square plus m3 r3 square plus and so on plus mn rn square. m1 is at a distance of r1, m2 is a distance of r2 and mn is a distance of rn. Therefore, I is equal to, when you apply sigma over the summation, you will get sigma mr square. Sigma mr square. Moment of inertia about this axis of rotation can be written as I is equal to sigma mr square. Consider a plane lamina. X and Y are two mutually perpendicular axes. X and Y are two mutually perpendicular axes. Z is an axis which is perpendicular to both these two mutually perpendicular axes. As we have seen, y and x are two mutually perpendicular axes. Now let us consider the moment of inertia about z axis Iz. Moment of inertia about z axis Iz. Now let us consider one more point P on the plane lamina whose coordinates are x and y. We are calculating the moment of inertia at this point and this is extended throughout the entire body. On applying Pythagoras theorem, OP square is equal to OA square plus AP square. That is, R square is equal to X square plus Y square. The process of calculating the moment of inertia is extended throughout the body. We are applying sigma. Sigma mr square is equal to sigma mx square plus sigma my square. Sigma mx square is equal to iy. Sigma my square is equal to ix. Therefore, iz is equal to ix plus iy. Inertia of a lamina about an axis perpendicular to its plane and passing through a point is equal to the sum of the moments of inertia about any two axes in that plane which are mutually perpendicular and passing through that point. Here Iz is the moment of inertia about a perpendicular axis to the plane lamina, and Ix is the moment of inertia about an x-axis, and Iy is the moment of inertia about y-axis. Therefore, Iz is equal to Ix plus Iy. Ix and Iy are two mutually perpendicular axes. Now let's move on to the parallel axis theorem. According to it, the moment of inertia of a rigid body about an axis passing through O is equal to the sum of the moment of inertia about a parallel axis passing through its center of mass and product of mass of the body and the square of the perpendicular distance between these two parallel axes. Let AB and EF be two parallel axes which are separated by a distance r. Let I and Ig be the moment of inertia of any axis and the moment of inertia about the center of mass respectively. Now let us consider a point P which is at a distance of OP from the axis of rotation AB. The right angle triangle OPD, OP square is equal to OD square plus DP square, but OD is equal to OG plus GD. OP square is equal to OG plus GD whole square plus DP square. Therefore, OP square is equal to, and applying the formula A plus B whole square, OG square plus GD square plus 2OG into GD plus DP square. Therefore, OP square is equal to OG square plus GD square plus DP square can be written as GP square. Therefore, OP square is equal to OG square plus GP square plus 2OG into GD. On applying the sigma, you can find out the moment of inertia of the lamina about an axis passing through, that is I. The bracket term indicates sum of moment of inertia about center of mass which is equal to 0. Therefore, m OP square is equal to I, sigma m OG square is equal to IG, sigma m GP square is equal to MR square. Therefore, I is equal to IG plus MR square, where I is the moment of inertia about any axis, Ig is the moment of inertia about an axis passing through center of mass, and m is the mass of the body. R is the perpendicular distance between these two parallel axes. Therefore, the moment of inertia about an axis, about any axis, is equal to sum of the moment of inertia about an axis passing through center of mass and product of mass of the body and square of the perpendicular distance between them. Hence, parallel axis theorem is proved.